Okay, so the first model we will introduce is going to consist of two compartments. Okay, but we before we start writing equations, we have to make assumptions. Okay, so we're going to derive this model. We're going to first assume that there is a population that has n, capital N individuals, and also that these individuals are mixing homogeneously at random. So we're going to assume that this population n, so think of, we have a population of size n, but now think that this population of size n is actually split here. You can think of this being divided into two groups. Okay, one group is going to be called S, and the other group is going to be called I. So this is the idea. You have one population of a specific size, a number of individuals, and now you think that these individuals may actually be in one of two groups, and you label or classify or name these groups according to the status, the so-called epidemiological status. Okay, S is going to denote individuals that are healthy and are not infected. So typically they are called susceptible. And I is going to denote the group of individuals that are infected, and we're going to assume that they are both infected and capable of passing the infection immediately. So we assume they are infected and infectious. Okay, so we assume we have two groups. So we have I, those individuals that are capable of passing the infectious agent. So we call the I individuals infectious. And then we have those who are not infected, and they are denoted by the letter S. This is the illustration I showed you at the beginning. N is split into S and I. So we're going to say S plus I. We're going to assume that S added to I adds up to the total size of the population. So every individual in this population, we're going to assume that every individual has, on average, the same number of contacts. Okay, so we're going to assume that an average number of contacts B is the same number for every individual in this population of capital N individuals. Okay, so we're going to assume that B here denote that average number of contacts per individual. So if B denotes, let's write something here. So if we have that B denotes the average number of contacts per individual, then we can say that I over N is the fraction of infectious individuals, and therefore this product, this quantity B times I over N denotes basically the budgeted amount of those average number of contacts, how many of those are budgeted to individuals in the I group with infectious individuals. So when we multiply that average number times this fraction, we're basically correcting the average number, and this quantity gives us how many of those contacts are spent, how many of these contacts are spent with individuals in the compartment we're calling I, in the I compartment. Okay. Another note here is that we are assuming homogeneous random mixing, right? We're assuming random, but when we say random here, we mean uniformly at random. Uniformly at random means unbiased, right? So having this term I over N, it's also not a coincidence. That is exactly consistent with the assumption of unbiasedness, right? There is an unbiased chance to encounter individuals in the I compartment. So we have that B times I over N is how many of the average number of contacts are spent with I individuals, and this would be, remember, B is the average number of contacts per individual. B times I over N is the fraction of the average number of contacts per individual that are spent with I individuals. Now, if we add up that over the number of individuals in the S compartment, then this quantity S times B I over N, so basically this is what's happening. We start with an average number B. This B is corrected by how many of those contacts are spent with I individuals, and this gives us a quantity per individual, and now we add up that. We have S individual in the S compartment, so we have the quantity S times B times I over N. Okay, so this now gives us the total count of contacts obtained when adding up over all individuals in the compartment we're calling S. So we have B S I over N. So basically this quantity is the total number of contacts between individuals in both of these groups. Okay, this is a rough count though, because remember we started with the assumption that B denotes the average number of contacts, and that average number of contacts is the same for all individuals. Okay, so this is a rough raw estimate or rough count of the total number of contacts between individuals in the S compartment and the I compartment. Now, let's consider that quantity, B times S times I divided by N, but let's now consider that quantity multiplied by this quantity here, P. Okay, P is going to denote, this quantity here is going to denote, P is going to be the probability that given a contact, probability of infection, successful infection, basically probability of infection given a contact. So in our introduction to this topic, we discussed that there are different modes of transmission. There are different according to the pathogen, there are different ways. There are some pathogens that are airborne. There are other pathogens that are transmitted by sexual contact. There are other pathogens that require a vector, which is an intermediary. So not every contact is successful in carrying on or passing on the pathogen, right? So even though you may have contacts between those individuals that are carrying the infectious agent and those individuals that do not have it, that doesn't mean that every contact is going to lead to an infection. So there is a degree of randomness there. There is a degree of uncertainty, and that's precisely what this parameter here, P, denotes. It denotes the probability of infection given a contact. So what we're going to do is that we're going to say, so we're going to take this expression here. We're going to say, let beta denote P times B, or B times B. So B is the average number of contacts, P is the probability of infection given a contact. And now this parameter beta is going to be called the transmission rate, the rate at which infection is passed on. So this is a rate, it's going to have units of 1 over time, okay, but we're going to assume that B times P is denoted here with beta. So we have this expression. We have the expression beta times S times I divided by N. And this expression is what will be called the number of new cases of infection.